Hello, in this video we'll talk about matrix manipulation in Matlab as well as even and odd signals. We'll first introduce a few commands that are useful in Matlab to manipulate matrices as well as built-in functions. Next we'll talk about the TickTock command, conditional statements in Matlab, and finally even versus odd signals. This slide lists a few useful commands in Matlab, some of which we have covered already before in previous videos, but I will still go over them and do some examples on some of them and introduce new ones as well. So the first command extracts or displays for us the element at index n from A. If we want more than one element from A, we have to specify their locations or their indices. So the command here will display elements at index 1, 4, and index 7, assuming A has a length greater than or equal to 7, of course. The command A at n is equal to x will change the value in A at location n and assign it a value to equal to the value of x. So let's do examples on the top three commands. The first thing we will do is to create a new script file. If we want to save our work, I will add a comment with my name. Start with CLC to clear the command window, clear all to delete all the variables, and finally close all to close all the figure windows that you might have open. Okay, so we'll start with creating a variable named A with some random values just to experiment with A. I'm gonna make sure this one is different so it's unique and it's easier to test. So this is matrix A or vector A. Calling the command A3, for example, will display the third element in A. Once I run the file, it will ask me, Matlab will ask me to give it a name for the first time. So the output window or the command window displayed for me the array A, and A3 gave me the third element in A, which is 1. Calling A 4, 2 will give me the fourth element, which is 10, and then the second element in A, which is 3. So I will expect to see 10 and 3, a new array created with elements 10 and 3. Okay, if I say A3 is equal to 0, this command will change the third element in A to 0. So if I click run, the third element in A will become 0. Doesn't have to be 0, you could put any value and then it will update matrix A. If you want to change more than one element in A to 0 or to any other value, you can specify the elements here. So I'm going to say A from element 4 until the end. I want to change them to 0. So from element 4 until the end. So instead of 10, 8, 9, I will see 0, 0, 0. So if I click run, this is what you're going to see. Okay? But pay attention to the fact that if you try a different number like 2, this 2 will be also the new values for each of the last 3 elements. So even though I provided one number, Matlab will assume that all of these values, you want to change them to the new value, which is 2 in this case. Okay. This command right here will set the elements in the first column of A to all zeros. We're assuming here that A is actually a matrix or a two-dimensional matrix. So I'm going to erase all of these commands, change A such that it's a matrix of size, let's do 3 by 3. This is how to create a matrix in Matlab. You separate elements using a space or a comma if they're in the same row to create a new row, you use a semicolon and or a new line of code. So if I click run, I will see A is the 3 by 3 matrix whose elements are given by what I specify. So calling the command, say colon, comma, 1 will display the first column in A, okay, which is 6, 10, and 5. If I call A, the same command, but assign it a value equal to 0, this will reset all the elements in the first column in A. So it modified A for me such that the first column has values equal to 0. So this is what this command will do. Similarly, if I want to change the last column in A, I have to say end. A colon, comma, end. So this is their last column in A, changing the last column in A to zeros. The next set of commands, some of them we know already. For example, t is equal to -2 until 3. So this will create a matrix or an array whose elements are -2 increment by 1 until we reach 3. So this is the value of t. Y is a function of t, and it's expressed as 2 times t. So this is the result of y. Here I'm creating a new array named t, and I'm comparing each element in t. I'm creating a new array named n actually, and I'm comparing each element in t with 0. I'm checking whether each element in t is greater than or equal to 0. So the values of n are either logical 1 or logical 0. I can use n instead of indices numbers to extract elements from y. So wherever n is logical 1, I will read the values from y. So I'm going to ignore -4 and -2 because n is 0 at these locations. I will only output 0 to 4 and 6 from y because now I'm using logical values instead of indices to extract elements from y. You can experiment with this in Matlab to help you further understand it. The next useful function we'll use is the flip-lr. Flip-lr is actually short for flip left to right. So let's try it on a new variable, say named v, and v is an array starting at -3 until we reach 5. Calling flip-lr on v will simply flip v from left to right and output the result. So v is -3, 2 until 5. Flip-lr v actually starts at 5 and then 4, 3 until I reach -3. So I simply mirrored the vector v. The next built-in function that is useful is the I function, or the identity matrix function. It will create an identity matrix for me of the given size. It can take 2 inputs or 1. So if I give it 1 input, it will assume you want a 4 by 4 matrix whose elements are all zeros except ones at the diagonal. Similarly, you can call I 4, 4. These two commands will give you the exact same result. But if you want a matrix whose elements are all zeros except ones at the reverse diagonal, then of course you can call flip-lr on I and choose the number of elements you want in the row, or basically the size. See the difference between I and flip-lri? We have ones at the reverse diagonal right now because of flip-lr. So we flip the entire matrix from left to right. The next command is, or operator, is actually the tilde operator. which will flip the 1 into a 0 and will change the 0 into a 1. So let's try tilde on 0. The output of this will be 1. Tilde on 1 will be 0. If you have a vector named, say, x, whose elements are 0, 0, 1, 1, then calling tilde x will simply give you 1, 1, 0, 0. Okay, so let's use the I as an example. I will run the script. I will give you zeros everywhere except ones at the diagonal. Then calling tilde on I will give you ones everywhere except zeros at the diagonal. This command can be useful if you want to reset the values of a matrix, or reset the values in the diagonal of a matrix. So if you have a matrix named A that's of size 4 by 4, some random values, so A is of size 4 by 4, calling A dot times I 4. Remember to put the dot here because we want to perform element-wise multiplication. So A dot times I 4 will make sure that you keep only the elements at the diagonal from A. All the other elements will be reset to 0. Why? Because the I matrix has zeros everywhere except ones at the diagonal. So 0 times 8 is 0, 0 times 9 is 0, and so on. Only at the diagonal you'll have ones, so you will keep the numbers the same, because 1 times any number is that number. So 1 times 4 is 4, 1 times 6 is 6, and so on. If you want to do the opposite, which means you want to keep the diagonal, reset the diagonal elements to 0 and keep everything else, then you have to flip the I matrix first, or actually flip the bits in the I matrix first. See the difference between this and what we had earlier? So these are other commands that you can experiment with. It's the exact same thing we just did. Next is the TickTock command. All this command does is that it counts how much time, or it counts how much time Matlab takes to compute certain operations. So let's start by creating let's do tick and then talk. We want to perform the sum between, or calculate the sum between 5 and 25, and then this time we want to do it using a for loop. So let's try s is equal to 0, that's our temporary variable, and then in the for loop I want my iterator to start at 5 until 25. I'm gonna add to s the new value in n, so n plus s, and then end. Once I exit the loop, I'm gonna display the result. I will enclose this with or between tick and talk. So we will have TickTock to surround the sum command and another TickTock to surround the for loop summation. I will click run now, and you will see how much time it took Matlab to calculate each of the sums. Turns out the sum command is faster than calling the for loop. So that's how the TickTock command basically works. Next is conditional statements in Matlab. The first conditional statement is the if statement. You can check the help if command in Matlab to tell you how to use it. So I'm going to type help if. It will give you details on how to use the if statement. The command is very simple. You just type if, and then the condition, the statements you want to perform, followed by else if you have a second condition to check for, the condition, then the statements you want to perform, and then the else part will contain, of course, the default statements. Remember to close the end. So else if is one word, and remember that else if and else are optional, but they are recommended to include within your code. Next is for loops. We already talked about for loops previously, but in brief, or to recap, you just have to start with for, remember to end the for loop, and then include your iterator, I is equal to 1 through n. So the first time you enter the loop, I is equal to n, and so on. You can have nested for loops like this. So for the first iterator is I, then the second for loop, or the inner for loop, has an iterator named C. Alright? This is another example where we're iterating through the array x. So we're starting at index 1 until the length of x, which is the last element in x. The last loop we'll cover is the while loop. Knowing the for loop is sufficient, but it's useful also to know how to use the while loop. So the way the while loop works is that you'll have to check for the condition first. So you have a condition. While that condition is met, you will keep iterating through the loop, or you will keep repeating the commands within the loop. Once this condition is no longer met or true, you will exit the for loop, the while loop actually. And here you have an example on how to use it. So you have to have while, the condition, and then the statements you want to call, and end the while loop with the end statement. So as an example on for loops, I will do the I function from scratch. So we know the identity matrix is a built-in function that takes the size as an input. You can either give it n, and it will assume you want to create an n by n matrix, or you can give it n, the number of rows and the number of columns that you want, like this. I'm going to create my own user-defined identity matrix that only takes one input. So for this, you could either use the function template, click on new function, modify this such that it works for your own purpose. I'm going to call it my I. It should take one input named n, and it will output one output. I will call it y. Within the function, I have to define my output. I will start by creating an empty matrix. Not empty, it's actually a matrix of all zeros. So I'm going to use the function zeros with the size n. You can use n by n, or simply n, and it will assume you want an n by n matrix. So I'm going to do n comma n. So we want a matrix of size n by n, whose elements are all zeros. And then in the identity matrix, all the elements are zeros except ones at the diagonal. So now I have all the elements are zeros. My purpose now is to set the elements at the diagonal to ones. So I will use a for loop for this purpose to iterate through each element in y. So I'm gonna say I is equal to 1 until n, because that's my size, the row number, the number of rows at least, and then end. Remember to end. So what we'll do is assign the elements at I, meaning where the row number is equal to the column number in y. We will change the. This is one way to write the function. I will copy it paste it at the end of the file, and then test it above it. So I will call my I on size 5. Now we'll run the file. We should have two outputs. One is from I, the built-in function, and one is from my I. Both should be identical, and I can try it with other sizes as well, and it should work. Okay. The other method I will implement the my I function is using nested for loops. So I'm going to iterate through each row and each column. So I'm going to create a new variable named k, or let me call them R and C. So R is the number of rows, the row number, C is the column number. So from the first row until n, from the first column until n. So I'll have to end this for loop, the inner for loop. Within the inner for loop, I'm gonna use an if statement to check if the row number is equal to the column number. Then I want y at r comma c to equal to 1. And then remember to end the if statement. So this method requires the use of two for loops or nested for loops and an additional if statement. This method can be useful if you want your function to work with two inputs as well. So it will be exactly similar to the identity matrix that is built in, the identity function that is built in Matlab. So both functions, this one and this one, are valid. I'll keep this one as it's simpler. Okay, so this is an example of using for loops and if statements, or the conditional statements in Matlab. The last topic we'll cover in this video is even and odd signals. In general, even signals are symmetrical along the y-axis. So this is an example of an even signal. Odd signals, on the other hand, are symmetrical along the origin point. For any signal, you can extract the even part of the signal by simply calling the expression or the formula y even, or the even part of the function y, is equal to y of x plus y of negative x divided by 2. So you're adding this point to this point because that's y of minus x, that's y of x, which is in this case y of minus 5 and y of 5. You add them together first and then divide by 2. This will give you the even part at this point. Remember, this is just a mathematical expression, it's not Matlab code, so we'll have to translate it to Matlab code. To get the odd part of a function, you have to use the formula y odd, or the odd part of y, is equal to y at x minus y at minus x. Everything is divided by 2. When I said everything, I meant that here subtraction has the highest priority, so that's why it's placed between brackets. And then you divide the answer by 2. Remember that, again, y of x in Matlab is simply y. Because if you type y of x, Matlab will assume you want to extract the x element from y, which is not really the case. You simply want the entire array of y, which is a function of x. So to obtain y of minus x, you simply call the function flip LRY, because y of negative x is simply the inverse of x. So for this, the inverse of y. So for this part, we will call flip LRY, flip left to right on y. So let's see examples of even signals that we are familiar with. The absolute function, for example, f of x is equal to the absolute of x, which looks like this, is an example of an even signal because it's reflected along the y-axis. The cosine function is also an even signal. From the shape of it, you can see that it's reflected along the y-axis. So it is an even function or an even signal. G of t is equal to t squared is an even signal. As a general rule, t raised to the power of any even number is also an even function. For example, t raised to the power 4, t raised to the power 6. These are all even functions. And remember, to get the even component of a signal, you call y of x plus y of minus x. This is the numerator. In the denominator, you put 2, or you divide this part by 2. So remember to put the brackets here. Since these signals are purely even, then they do not have an odd part. So the even part, or the even component of these signals, is exactly the same as the signal. Examples of odd signals include f of x is equal to x, y of x is equal to sine of x. So the sine function is an odd signal because it's reflected along the y-axis. gt is equal to t cubed, or t raised to the power 3, is an odd function. Again, as a general rule, you can say that x raised to the power of any odd number is an odd function. Here it's x raised to the power 1, and 1 is odd, so this function is odd. Or from the shape of it, you can tell it's an odd signal. 3 is an odd number, so t cubed is an odd signal. Similarly, you can obtain the odd part of any signal by applying the formula y at x minus y at negative x divided by 2. Since these signals are odd, they don't have an even part. So the odd component of these signals is equivalent to the signal itself. One feature of mixed signals, so there might be signals that are a mixture of both even and odd signals, or there might be signals that are neither even or odd, which is this an example of. So if you add the absolute function to x, you'll get something that looks like this, which is neither even or odd. It's not symmetrical along the y-axis, it's not symmetrical along the origin. However, if you apply the formula we learned for extracting the even part of the signal, which will give you, of course, the absolute function. So f even is equal to f of x plus f of minus x, everything divided by 2. This will give you the absolute function, or a signal that looks like this, which is actually the absolute function. If you apply the formula that gives you the odd part of a signal, you will get x, or a signal that looks like this. Summing the odd part with the even part of a signal must give you back the original signal. So you can extract the odd part first, then extract the even part, sum the results, and that should give you the original signal. These are the formulas we saw earlier. So let's understand how we can implement them in Matlab. We said that y of x in Matlab is simply y. So the variable y, and we can add as a comment, this is a function of x, or a comment y of x. To get the reflected signal y of minus x, we have to call flip LR on y. So we already know y, we know how to get y of minus x. Simply call flip LR y. Then translating this formula into Matlab code gives us y even is equal to y plus flip LR y brackets divide by 2. To get the odd part, you can copy this line of code, simply replace the plus with a minus, because that's the only difference. Okay? Remember that these formulas assume that the signal y is centered on the x-axis, meaning 0 is in the middle of x, and then the signal x is symmetrical along the x-axis. For example, it starts at -4 and then ends at 4, and 0 is in the middle, and so on. What if the signal is not centered on the x-axis? Meaning, what if x starts, say, at -1 and then ends at 3? So think of this and think of a way to implement this in Matlab. Okay, now we'll create a function as an exercise that extracts the even part of a signal. I'm gonna do this as a function. Okay, so let's erase all of these. Okay, so the function, I want to call it even signal, for example, or even sig, that takes any signal. So as an input, I will use signal, and outputs the even part. Remember, the formula is very simple. The even part, make sure to spell it correctly, uppercase P. So the even part is equal to the signal plus flip LR on the signal, everything divided by 2. So remember to put brackets around the numerator. You don't have to use this variable, you could use any variable name. So I can use y just to match what we see in the slides. So this variable is local to the function. So whatever name you use, you have to be consistent within the function. And when you call the function, make sure to put it in the right location. So this is the even part of the signal, assuming y is centered around the x-axis. To create a function that extracts the odd part, I will copy this function. I will just rename it to odd signal. The output, just so that it's descriptive, I'm gonna call it odd part. Here I will say odd part is equal to, simply change the plus to a minus. And that's it. To test this function, I'm gonna create some signal named y, and y is equal to x plus the absolute of x. Okay, and x can range between, for example, -10 to 10. In this case, x increments by 1, and that is fine because my function is actually linear, so an increment value of 1 is sufficient. And remember that I don't have to stick to this name. I can use f of t or y of t. So let me use y of t. So y of t is equal to t plus absolute of t. As a comment, you can add y of t is equal to t plus the absolute value of t. So this is how to write the expression in math. And again, you can write as a comment here, the even part is equal to y plus, or actually y of x in this case, or y of t, plus y of minus x, everything is divided by 2. Here it's the same, except you put negative here instead. Okay, now we'll try to call the even part. So I'm going to call it even, or y even is equal to even signal on y. Y odd is equal to odd signal, where the input is also y. Now I have the original signal, the even part of the signal, the odd part of the signal. I will use subplot to plot each of these 4. So we'll start with the original signal, the even part, the odd part. Since we mentioned that the summation of them, so I will call it y total, is equal to y even plus y odd. The summation must match the original signal, which is y in our case. So I'm going to create subplot of size 4 rows by 1 column, because I have actually 3, 4, the original, the even part, the odd part, and then the summation. So I have 4 total plots to look at. First one will be a function of t, so y of t. X label is y, or t actually. Y label is y, and this is the original signal, original y of t. For the rest, since there's only minimal changes that I will make to the line of code above, I will simply copy paste it and then modify it. So the the location is the only thing that will change for subplot. This time I'm gonna plot the even part, y even, and this is y even, or the even part of y, even component of y of t. Third plot is the odd component, so y odd, with or without space, doesn't matter, and I will call it y, the odd component of y of t. The last thing we'll look at is the summation of the even part and the odd part, so y total. I will call the or the y-axis y even plus y odd. So this is odd component of yt plus even component of y of t. I'm gonna click run. Hopefully there was no errors, but there is. Let's fix the error. So this question says we have a problem at line 75. When calling a function or indexing a variable, use parentheses, otherwise check for mismatched delimiters. So it's in this line. Actually, I forgot the brackets without even trying to understand the message. I just noticed right away that title is a function, so I have to close the brackets. We'll try to run it again. If there are errors, we'll fix them. So we're expecting to see one figure window, which includes 4 different graphs. The original signal, which is the t plus absolute of t. That's the even component, which is the absolute of t. This is supposed to be the odd component, but it's not. And this is the summation. Summation looks like the original, that's good. It looks like I forgot to edit this part, y odd, which is why testing our code is very crucial. So y even, y odd, y total. Now that should be the correct code. This is the original signal, the even part, the odd part, which looks like x or t in our case. So y odd is equal to t, because the original signal was simply t plus absolute of t. So the odd part of that is t. The summation should give you back the original signal. Again, as an exercise, think of what if the signal y is not centered on the x-axis. Again, remember what this means is that t ranges between, or let's look at the graph even better. So t ranges between -10 and 10, and the signal centered around 0 in the x-axis. There might be cases where t actually starts at, say, -5 and then ends at 10. In this case, the functions that we wrote here will not exactly work correctly, so they're not going to work as desired. That means we'll have to modify the implementation of these to make it work. But whenever y is centered around the x-axis, then this code is sufficient. This slide summarizes some useful commands in Matlab, some of which we did not mention in this video, but they're still useful, such as the diagonal function. Diagonal A gives you the diagonal elements in A. If the input to diagonal is an array rather than a matrix, then the output of this is going to be different. It will give you a matrix. So you can try experiment with the ones we did not cover in this video. Another useful function is the round function, which will round the number to the nearest integer. The remainder function and the modulo function are also helpful to, for example, figure out the remainder of division. So this will be useful when you solve some of the exercises in this lab, to be particular for exercise 1. So you could use remainder or modulo, the modulo function. This is all there is for this video. If you have questions, you can email me.